Okay, with partial derivatives, which is what we're going to talk about now, we examine a function of n variables as a function of one variable at a time and holding the others constant. So by exact definition, we're going to say the derivative of f with respect to x, let's just do two variables, is the limit as h goes to 0 of f of x plus h y minus f of x y all over h. So if you want to use the exact definition, if it exists, that's what it is, and the partial with respect to y will be the limit h approaches 0, f of x, y plus h, minus f of x, y, all over h. And that's similar for a function of n variables. Now we can also write f with the derivative of f with respect to x as the partial, and that's a funny d. You tell the difference between a regular d, so we know that's a partial derivative. Or since f of x, y is z, we could say it's dz, the partial of z with respect to x. And same for fy. It's partial of f with respect to y. Or we could write that as partial z with respect to y. And there's a lot of other different ways you could write these. So for an example, if our function is this, and we want the derivative of it with respect to x, the partial, here we're going to hold y constant. And just look at x as a variable. So if y is constant, this first term, well, let's just take the derivative of each. I'll just use a prime here. Each one. And if y is constant, that's going to be 0. And here, 3y is constant. So when you have a constant, that's just going to be minus 3y times the derivative of x, plus, and the derivative of x with respect to x is going to be 1. So this is just going to be minus 3y, because derivative of x is 1, plus 1. Now, that prime notation is not really correct, but it's just so you know that we're taking the derivative. We really should use better notation. Now, if we do it with z with respect to y, here we're going to hold x constant, or fixed. So, again, taking the derivative of each one, but this time x is constant. All right. Okay, so the derivative of 2y squared with respect to y is 4y. This is a constant, so that just stays out in front. We're taking the derivative of y, and x is constant, so that's 0. So this is just going to be 4y, derivative of y is 1, minus 3x. So this is with respect to y, the partial, and this is the partial with respect to x, for an example. Okay, now let's try to draw a picture. If we graph the function, is a surface. So if, let's take y as constant, say y0, then we have z equal f of x, y0, and that's the equation of the trace of the surface in the y equal y0 plane. So the trace is represented by y equal y0 and z equals f of xy, which is the intersection of those two curves. And so the first one, this one right here is a plane, and this right here is a surface, and their intersection is the trace of this curve, or of the surface. So if we do the partial at x0, y0 with respect to x, then that's the slope of the tangent line to the curve, or the trace, at the point x0, y0, f of x0, y0, and the plane y equal y0. Okay, so let's sketch this. X, y, z. And let's say x0's here, y0's here, and okay, let me draw this surface. This is z equals f of xy, and this point right there in red, let me draw it red, is x0, y0, f of x0, y0. And this is the tangent line. So let me say the surface goes like this. This is an infinite surface, of course, and the tangent line in that plane is going to do that. So this is the trace. And the slope of that tangent line is going to be df dx. Now, df dy at that point is the slope of the tangent line to the trace, having the equations x equal x0, so that it's in the x0 plane. At that point, in the plane x equal x0. So when we draw that, draw it in green, this is the x0 plane. So the tangent line is going to kind of go like that. And it'll be parallel to the y-axis. So that this green one will be parallel to the y-axis, and the blue one is parallel to the xz plane, or the x-axis. And the slope of that tangent line is df dy. Okay, so those are kind of hard to draw, but I think you can kind of get a picture of what's going on from those. Another way to think about the partial of f with respect to x is the rate of change with respect to x when y is fixed. So remember, derivatives are a rate of change. And same for the partial of f with respect to y. It's the rate of change with respect to y when x is fixed. So let's try another example. Let's let our function be e to the y cosine x plus ln of x y, or x times y. Let me rewrite this. ln of xy. So the partial of f with respect to x, here y is a constant, so that means e to the y is constant. So we're just going to take the constant is going to stay out in front, and just take the derivative of cosine x, which is minus sine x. Now the derivative of ln, remember, is the function goes in the denominator and the derivative is in the numerator. But y is constant, so we're just taking the derivative of x. So the derivative of yx is just y, because the derivative of x is 1. So this is minus e to the y sine x plus 1 over x. And we can do it again. Let's go back to black. We can take the second partial, again with respect to x. And again, e to the y is constant. Y is constant, so we have e to the y, the derivative of sine is cosine. The derivative of 1 over x is minus 1 over x squared. So this is a constant. We're just taking the derivative of sine and the derivative of 1 over x. Okay, likewise, we can take the partial with respect to y. Here, x is constant. So that means sine x is constant, or cosine x is constant. So again, let me write our function so we can reference it. So this is a constant. Let me just use k for constant. So we just take the derivative of e to the y, and that's e to the y. So here we have cosine x, constant stays on front. Derivative of e to the y is e to the y, plus the derivative ln, the function goes in the bottom, the derivative goes on the top. Derivative of y is 1, x is a constant, so this is just x. So this is going to be e to the y cosine x plus 1 over y. And we can take the second derivative, partial derivative with respect to y. We just take the derivative with respect to y again. The derivative of e to the y, this is constant. Derivative of e to the y is e to the y. Constant just stays. derivative of 1 over y with respect to y is negative minus 1 over y squared. All right, now it can get a little tricky when we write this with respect to y, then with respect to x. So first we do y, then x. So this is first, and then the x is second. So again, our original function was this. Let me rewrite it. So first we take it with respect to y, and that was this. Okay, we already did that. And now we take this with respect to x. So y is a constant, so this is going to be e to the y. If y is a constant, then e to the y is constant. The derivative of cosine x is minus sine x. And the derivative of this of 1 over y with respect to x is 0. So this is just going to be negative e to the y sine x. And we also can write this as f of yx. So notice this is what you do first, then this is second. But here, this is what you do first, and this is second. So it's reverse order. That's what makes it a little tricky. Then we can do so again, with respect to x is first, and this is second. We can also write this as f of xy, where this is first, and this then you do y. Okay, so with respect to x, we had this. Now we take this with respect to y, so x is a constant. This is going to be a constant. So the answer to this is going to be sine x. Derivative of negative e to the y is negative e to the y. The derivative of 1 over x is 0 since x is a constant. So this is negative e to the y sine x. Now notice in this example, it's really important that f of xy is equal to f of yx. And we'll see why in a minute. That's not always true, but frequently it is. So let's look at this theorem. I'll explain why it's true. Okay. All right, I fixed it. Theorem. Let f be a function of two variables, x and y. X and y, and as a function of two variables, x and y, defined on an open disk containing the point x0, y0, and the partial with respect to x, partial with respect to y, xy, and f of yx are also defined on that disk. And f of xy and f of yx are continuous on this disk. Then the conclusion is that f of xy at that point in the disk is equal to f of yx. So in order for those two to be equal, all the partials have to be defined, but also the second partials, fxy and fyx, have to be continuous, and then you'll get that equality. Okay, so to see more examples, look at some of the homework problems that I've done for you in the example homework.